to carry out that particular discussion, what morning was discussed. Is it that only we are having, this advantage? Certainly not. We are able to perform calculations moving from real numbers to the complex numbers. So yesterday morning, yesterday afternoon, today morning, what so far you have seen, rather than the real numbers, everywhere you are finding the complex numbers, right? In fact, a real number itself is a complex number, right? Where in which your imaginary field is 0. So actually, we are dealing with the complex numbers. Even in the real world also, we are dealing with the real numbers which are complex, but we are nullifying that imaginary value, and because of that, we are saying real numbers. Right, anyway, so the quantum computing or mechanics is different from the other branches in the way we are using the complex numbers. Okay, of course, complex numbers are already there in the various applications, but how we are using to represent the state of a qubit. Okay, that is where these numbers. Then from single state to the superposition states. Yesterday was discussed, morning also was discussed. So from single state, we move to the superposition states, right? So every object exists in a unique place and in a well-defined state, even when we are not looking at it. That is what in the classical listing. So meaning what? You keep some object stored, even if you don't observe it, it will be in the same state. Whereas in the quantum, it tells us that it is false for objects that are very small. Meaning what? Small kids what? If we don't observe, what they do? They do naughty things, right? So they will not be in the place. If you ask them to sit here and then do, no, they will not sit. They will be doing a lot of naughty things. So it's like, so when you go to that, for that small thing, what was the technical terminology they said in the last 2 days is subatomic level, right? Microscopic level. When we go to that level, objects will not be in a well-defined state. Rather what? They will be in a doing some activity, right? And because of that, we are saying that we are moving from single state to the superposition of states, right? It is simultaneously in being in multiple states at the same time. But what is the interesting aspect of it? The moment you observe it, they'll come to a state, which we call it as collapsing to one particular state, right? And we call it as a measurement. So when you don't measure it, when you don't observe it, they will be in multiple states. But the moment you observe it, they will come under one particular state. So to give, since all of us are computer science, to give an analogy, we know that fuzzy logic, right? So fuzzy logic, what it is, given an object, you define a membership function, then what happens? I am in a membership, I am in a fuzzy set of, even in engage, I can belong to a fuzzy set of kid, but with a membership degree 0, right? But with the membership degree 0, I will be in a fuzzy set of, say, middle age. So I am being in multiple states. So I can give an analogy to a fuzzy logic, wherein which I am there in multiple states. But when you measure it, so it comes under like, kind of a defuzzification. I'm just giving a crude example, right? Then we move from locality to the non-locality. Okay, best example, in operating systems, we deal with algorithms. We know that, a memory unit that is visited, it is most likely that the processor may visit, if you visit an ith location, you may visit I plus 1, I minus 1. But, whereas in quantum, you move from locality to the non-locality, wherein which, if you look at all classical science, objects are directly affected only by nearby objects. As I said, in operating system, we deal with the scheduling algorithms, right? So based on this particular philosophy. However, in quantum, the laws predict certain effects that work in a non-local manner. From where this non-locality is coming, people talked about the entanglement. right? Wherein which objects get entangled. Objects get entangled. The moment you try to measure one, it will affect the other qubit also, the state of the other qubit. So particles can be connected or entangled in a way that action performed on one of them have an effect on the other one. Now the point is, actually locality also affected, it's entangled, but it is about, even if it is the particle is at a distance place, that's what is the beauty of entanglement. And then deterministic laws, we are moving to the probabilistic laws, right? So to which specific state, we said, if you don't measure it, if you don't observe it, quantum state would be in a superposition of multiple states, linear combination of multiple states, if you don't observe. But what is the probability here? The probability comes the moment when you measure it, to which state it would get collapsed is the probabilistic nature. It is not deterministic nature, right? So whether it gets collapsed to the morning Sar was talking about, the computational basis, wherein which you have, on the north pole you have 0 and on the south pole you have 1. When you measure it, it falls to either 0 state or 1 state. That is probabilistic, right? It depends upon to which state it falls. It depends upon your amplitudes, right? So we said, if you have a qubit which is represented as alpha ket 0, beta ket 1, this is my qubit, right? This is my qubit. Then what happens? So to which state it gets collapsed is based on the square of your amplitudes, alpha square and beta square, right? So that determines to which state it gets collapsed. So from certainty to the uncertainty, this is another interesting phenomenon of quantum world, wherein which the laws of quantum mechanics informs us that there are inherent limitations to the amount of knowledge that one can ascertain about a physical system. Based on this, we have a principle. The other day, Professor Balakrishnan was mentioning about Heisenberg uncertainty principle. What is a Heisenberg uncertainty principle says? More accurately you know about a particle's position, the less accurately you know about its momentum, right? When an object has a momentum, if you wanted to determine its position in a very precise manner, how it is possible when you are having a moving train, if you wanted to precisely know what is the exact position of it, how do you know? Because it is moving, right? So that's what is the meaning of it. So the more you know about position, that means you are less calculating about its momentum. What is the example I said is the other way. The more you know about momentum, the less you can tell about its position, right? So and vice versa. From where this is linked, yesterday Professor Balakrishnan was mentioning about the wave-particle duality. Light being there in the condition of a particle as well as a wave, right? So these are the features of the quantum world. That is what actually makes quantum computers different and from the classical computers. So again, you can see that here we have a classical bit, and this is your qubit. Of course, morning Sar was talking about the block sphere representation. It's a sphere. You can see some dots here. You can think them as the qubit qubits, and you can see actually morning Sar was telling about the accurate or exact qubit states and the mixed states. Those things which are not on exactly on the sphere, you can think them as the mixed states. So a qubit can be represented. How you can represent a qubit? By a spin of an electron or polarization of a photon, right? So Sir was telling about in the morning about how to physically realize such qubits. There are technologies to, by implementing spin of an electron or by implementing polarization of a photon. After some time, we will talk about quantum key distribution, wherein which you will see in the QKD, quantum key distribution, you will see the qubits are exchanged in the form of polarization of photons, right? So like this, how do you implement them? Because now either Google is doing or IBM is doing, what they are doing is focusing on implementing, designing such qubits, right? So this is the one. So you can see that the electron spin. You can, morning Sir was talking about the representing in the form of a block sphere. Of course, it is a single qubit. So spin up, spin down. It's not only spin up, spin down for as an electron shown here, but it can have multiple states, right? So this is through electron spin up, spin down notations. And of course, you are having, as I said, photons being implemented as a light polarization through horizontal polarization and vertical polarization. Okay, so both would be used while sharing the key distribution. So in cryptography, one of the important problem is how two users, Alice and Bob, will have the common key when they wanted to interact in a symmetric encryption algorithms like AES. So people so far have used asymmetric algorithms such as RSA, Diffie-Hellman, elliptic curve to exchange the key. But quantum computers are breaking those algorithms. And because of that, now people are building qubits which are transmitting the information through polarization of photons. So you carry the information through polarization of photons, and hence, key can be exchanged. The beauty of such polarization is that the moment you send the qubits or the key in this way, either horizontal way or vertical way, if suppose an eavesdroppers listen to this, what happens? You are actually measuring the state. When you are measuring, what happens? The qubits comes to a particular determined state. So meaning you are collapsing the qubit state. So once if the qubit state is collapsed, both Alice and Bob will be able to know that there is an eavesdropper. Generally what happens? Eavesdropping is a passive attack. Meaning what? You do not know who is listening to the communication channel, because somebody is there listening to this channel. Now imagine somebody is listening to our conversation beyond the wall. How do you know? Until unless you go and see and outside. So it's a passive attack. So when you implement this exchange of information through this, since you attacker measures it, what happens? It gets collapsed. It gets collapsed. Both Alice and Bob would know that yes, Eve is listening to that. That is one thing. Second thing, morning Sir was talking about the no cloning theorem. Meaning what? Attacker wants to copy this. He cannot copy because the quantum states cannot be cut, copy, paste business is not there, right? So that's the beauty of this one. So sir, now if you see here, collapsing, when I say, it is the general usage term. In a quantum, we are saying it is a measurement. When I say measurement means what? When I measure this a qubit, it falls under either it belongs to the 0 state, as it was shown at the north pole, or it comes to settle down at the south pole. Okay. So to which pole it settles down, it determined by your probabilistic amplitudes. So the meaning of collapse is nothing but settling down to either a 0 state or a 1 state in your Z axis. Morning Sir was mentioning about Z axis, right? So this is Z axis. Now you have multiple axes. When you take it as a three-dimensional, you have x-axis, y-axis. This is computational basis, 0 state, 1 state. You have Hadamard states, right? One is called plus and then minus. Your measurement can settle down to this also. This is called your x basis. Now you have y basis, wherein which you have positive y, negative y. Your measurement may settle down to this also. Sir, it is not that why I should take z basis, x basis, y basis. I want to have my own basis. Of course you can have. So this is my A basis. This is my AB basis. If you want to measure it, you can define your own basis and measure it. Because you are having, as Sar was telling in the morning, when you think it as a sphere, you have infinite possible, you are about to ask something. So when I am sending the information, I am encoding in the form of qubits and I am sending it. Okay. When I am sending the information in the encoding in the form of qubits and I am sending it. So when I am sending it in the qubits, the other receiver, see, I have my 0. I want to send 0. In a classical channel, you will send 0. In a classical channel, you can send 1. But in quantum channel, I take 0, I encode it into the qubit, then I send it. And the receiver will take it, decode it, and get the bit. So now, what happens in this quantum channel? If the eavesdroppers listen, he is measuring that qubit, right, to get 0, 1. That will be known to the both communicating parties, because you are disturbing, as I said, you are collapsing from quantum state to classical state. When we discuss this, which one, sir? Correct. So when you take a superposition state, when you take a normal bit, you apply Hadamard, you get the superposition. When you apply Hadamard again, you will get into the classical state. Which classical state? We do not know. Which classical state? We do not know. That is one thing. So once the eavesdropper listen to that particular bit, okay, so the people, you are disturbing the quantum encoding, right? Once you disturb the encoding, then the either sides, it becomes like in your interruption, right? See, we are talking about interception and interruption. The moment you are measuring it, you are doing interruption. When you interrupt, what happens? Your attack will be like an active, so that what happens? Your both sides will know about it. Okay, that is the beauty of this the QKD part. That anyway, while talking about in the upcoming these things, we will see. So correct. What I said about the no cloning is, what you are talking is after measuring it. I am saying before measuring it. When it is in the quantum state, can I copy? So it is this. When we will discuss the no cloning theorem or no cloning this thing, and then we will prove that when I have, see, what do you mean by copying? Imagine that I have two qubits, x and y. What is meant by copying? I want to copy, see, what happens in our, you want copying this information to that, right? So I want to copy the state of this to this. Is it possible or not? It says it is not possible. Why it is not possible, we will discuss. What is your question? Sir, I have measured it. When I measure it, what becomes is your classic